Thank you to the organizers for inviting me to speak, and thank you all for sticking around for this session. In this 20 minutes, I'm going to try to briefly cover NVIDIA's perspective on quantum computing, and then what we're building to help realize valuable quantum computing. So the agenda looks like this. First, a very brief outlook focused on what we need to do to get to useful quantum computing in the future, and what different groups can be doing today towards that effort. Then I'll go into the two products NVIDIA is building now. Q-Quantum for accelerating and scaling simulations of quantum computers for research purposes, and Coda for integrating quantum computing with high-performance classical computing. And then wrap it all up with a little bit of future outlook. So starting with the quantum computing outlook, this figure was created by our partners at Google. I like it a lot and use it a lot. It maps out where we are now versus where we want to be in terms of number of qubits and the limiting error rate of the system. So on the left and on top, we have what's classically simulable. And you can really see if the limiting error rate is higher, we can simulate quite a bit more. And then there are these two regimes getting towards the bottom right. Useful error-corrected quantum computing, where we have millions of physical qubits so that we can have thousands of logical qubits, which are perfect so that we can run millions or billions of clock cycles. And then somewhere before that, we have the possibility of near-term applications. So in this conference, I'm sure you'll hear from very smart people who'll say that nothing matters except getting to this very lower right green region. And you also hear from very smart people who see lots of possibilities for value in this blue region. And no matter what your stance is on that issue, there are a few categories of things we know we need to improve in the next decade in order to get to useful quantum computing. So first, of course, is scale. We can do resource estimation and understand that to simulate an interesting problem, like Shor's algorithm for a useful number or a useful molecule, we'll need more qubits than we have now, at least hundreds or thousands. But that's not the end of the story. The limiting factor in practice is actually usually qubit quality. So for most known valuable quantum applications, we need to run for millions or billions of clock cycles. And if we need to do that, we need dramatically improved fidelity such that we can run quantum error correction. And running quantum error correction means that for scale, what we really need is not hundreds or thousands of qubits, but likely millions of noisy qubits such that we can have thousands of perfect qubits. And then there's speed. So we spent decades optimizing classical computers and making them faster and super efficient. And there's been lots of great research in recent years to show that an algorithmic quantum speedup is likely not enough. So if each quantum gate is 1 million times slower than the equivalent classical gate, then it's very likely that even if the quantum computer is good enough to be significantly faster, there's no advantage in practice. Now, all of these are improvements to quantum hardware that are needed, but it's not the end of the story. There's more that we need to do. We need to improve quantum software and algorithms, and really the quantum platform overall. So what do I mean by this? First, we need better algorithms. And this is true whether you're talking about NISQ hardware or future fault-tolerant hardware. So in this case, there's lots of interesting work in a huge number of domains, but more research needed to understand if, where, and how a quantum computer will be useful. And even in the fault-tolerant case, because of the huge overheads involved in pre- and post-processing and the gate speed difference between quantum and classical computing, many algorithms with quadratic speedups or algorithms for things like molecular simulation may not show an advantage in practice. So we need to keep developing better algorithms. We also need to figure out how to integrate quantum computing with classical computing. Especially today, while quantum computers are limited in performance, you'll want to offload as much as you can to the classical processors. And even long term, there are plenty of things that quantum computers will never do well. And so you'll want plenty of high performance classical computing in the loop. Today we see supercomputing centers especially leading the way in starting to figure out how to integrate these two and have quantum as a useful accelerator to their existing systems. And there's a lot of work needed in both hardware and software to understand how best to do this. And there's lots of discussion and lots of interesting points made at this conference on what groups should be doing in quantum computing now and what groups who are not building quantum hardware themselves can be doing. And I'll just point out that these are things that if you are investing in quantum computing or want to start investing in quantum computing, you can start understanding quantum better and realizing actual value now. And even if you are building a quantum computer, it's probably a good idea to be thinking about developing better algorithms and about how to integrate it with classical computing also. So at NVIDIA, we're not building quantum processors ourselves, but what we've already built is a full platform for accelerated computing. And what we do on the quantum team at NVIDIA is apply that and build on top of that to create value for quantum computing. And the two areas we work in are related to the two problems from the last slide. So first, we build tools for accelerating quantum circuit simulation. Our SDK for that is called Q2B. And what this enables is quantum algorithms research with high performance and at scale. And why that's important is because developing new and better algorithms is important, and today's quantum hardware is too limited to do that on real processors. So there's really a critical role to play for simulation. And the other effort is the integration of quantum and classical computing. So we see the future of integrated quantum computing as a place where you can write code in high-level languages and leverage CPUs, GPUs, and QPUs all together doing what they do best, and easily be able to port code from one piece of hardware to the other, and easily be able to estimate resources and benchmark simulated or real quantum processors to understand where and when quantum will be useful and start using it when it is. And we're building a quantum platform to enable that called Coda. So starting with quantum circuit simulation and Q2B. First, just a visual of why simulation is useful and important. So this graph is kind of a phase space of what you can explore with quantum circuits. The x-axis is scale, the y-axis is depth, and the lower left-hand corner is an area representing what you can access with QPUs today. So rough, but tens of qubits, tens of gates. So the two leading methods for simulating quantum circuits are state vector, which is kind of a brute force classical emulation of a quantum processor. So state vector simulation, you can also simulate tens of qubits, but an arbitrary amount of circuit depth. So thousands of gates, millions of gates, perfect qubits, noisy qubits, very, very flexible tool. And then kind of in the other regime is tensor network simulation. And so this is representing the quantum circuit as a tensor network, simulating it by contracting the tensors. And what this enables you to do is for many quantum algorithms, scale the simulation dramatically, so to hundreds or thousands of qubits. And I'll show an example of that later on. The cost with tensor networks is depth. So you can't simulate highly complex circuits, you can't simulate very deep circuits, but still it's a nice complementary method that allows you to explore how systems scale. So two kind of complementary methods, both letting you explore a much bigger space of quantum algorithms for research purposes. So our software for accelerating quantum circuit simulations is called Q2B. And the way that Q2B works is it integrates with the frameworks that exist today. So most people working on quantum computing are using Qiskit or using Cirq or using PennyLane or Amazon Bracket or one of these platforms like Stanwyck. And so Q2B sits beneath them all and it invisibly accelerates them on GPUs. So what it means for the developer is if you have a GPU and you install Q2B, you can do exactly what you were doing before, no code changes, and see some dramatic speedups. We also make a Docker container available called the Q2B appliance. What the Q2B appliance has been is the Cirq framework with Q2B underneath, optimized for 1 to 8 GPUs. And these numbers in the right here kind of give you an idea of the performance difference you can expect. So these are a few different quantum algorithms running on a CPU compared to the same algorithms accelerated by Q2B running on 1 to 8 GPUs. So even with one GPU, it's about a 10 to 70x speedup, and we see nice strong scaling. So you double the number of GPUs, the speedup is roughly doubling. up to a 70 to 300x speed up on 8 GPUs. So quite a big difference in terms of how fast you get work done, what you can simulate, et cetera. And we're happy to announce now that the cuQuantum appliance will now feature Qiskit integration alongside Cirq and provide native multi-node simulation, so the ability to scale to an arbitrary number of nodes, arbitrary number of GPUs. This means that scientists can now leverage, any size system up to an entire supercomputer as a single tremendously powerful resource for simulating quantum computing with a very kind of turnkey, ready to deploy container. And so to demonstrate this capability, we have 3 results here. The first is weak scaling. So one of the major limitations in especially state vector simulation is the need for exponentially more memory as the qubit count increases. That means for people working with these methods, qubit scale on a node is extremely limited. Not only is multi-node critical for performance, but for enabling larger scale. So here we're increasing the number of GPUs by a factor of 2, up to simulating 40 qubits, and you can see that the execution time stays very low. So showing great weak scaling, the ability to go up to supercomputing scale and still be able to run circuits very, very fast. For those with a fixed problem size but limited by execution time, so for example, a quantum machine learning algorithm that takes a very long time to train, the key question is strong scaling. So if I add more GPU resources, can I do this work faster? And that's what the plot on the far right is showing. So here we take a 32 qubit problem, which is the most we can do on a single GPU, and add more GPUs and show that we're able to dramatically reduce the execution time down to a couple seconds. So with all of this together, multi-node, multi-GPU enabled cuQuantum appliance on an NVIDIA accelerated system, researchers will see best-in-class performance compared to alternatives. So this plot on the lower right is, to our knowledge, the fastest multi-node simulator running on a 64-node CPU cluster, and we're about 3.5x faster running a quantum volume benchmark circuit with only 2 DGX A100 nodes. So the results from the previous slide were all state vector-based, multi-node, multi-GPU simulation results. This is just an example of what you can do with tensor networks. So not every problem is a good fit for tensor networks, but a lot of variational algorithms are, because they tend to be lower depth, tend to be lower entanglement. And so one great example of this is MaxCut. So last summer, a team from NVIDIA Research developed a novel variational quantum algorithm to solve MaxCut. And using that with cuQuantum, they were able to simulate up to a 512 vertex instance on a single GPU and up to 10,000 vertices with 93% accuracy on a supercomputer. So many orders of magnitude above what had been done previously, many orders of magnitude above what can be done on a QPU. A good example of how GPU-accelerated quantum circuit simulation enables you to study very large problems and how problems scale. As much as I'd like to, I've limited time, so I can't call out everyone's great results in using cuQuantum, but we're very proud to support a large slice of the ecosystem. So everyone from industrial research groups to quantum computing startups to academic groups to supercomputing centers. I like to say that NVIDIA is in a nice position where we aren't competing with anyone in quantum computing, but rather partnering with the entire community to advance the state of quantum information science. And so this level of adoption is a great testament to that. We're also seeing some nice examples of use cases in industry and success stories in industry. So BMW is using cuQuantum for their work applying QAOA to pathfinding and vehicle optimization. SoftServe is using cuQuantum for their work on quantum recurrent neural networks. Deloitte is using it for quantum natural language processing for materials research. And Johnson & Johnson is using it for studying a 7-mer protein folding problem, actually in collaboration with Stanwyck. So just a few examples that illustrate kind of the breadth of where simulation can be useful. So that was a very fast tour of cuQuantum. Now for a very fast tour of hybrid quantum computing and Coda. So the list of applications believed to be candidates for quantum advantage is large, but a critical consideration as we think towards quantum accelerated applications is that we know these will not execute exclusively on a quantum resource. They will be hybrid applications leveraging classical resources, doing the things that quantum computers don't do well, and working together with the quantum computer. This observation that today's scientific computing applications are candidates for future quantum accelerated applications in drug discovery, chemistry, finance, and optimization is more important than it may seem at first glance. And it gives rise to some big questions around, or big questions for those who are looking to prepare for a quantum accelerated future. So much of the effort today in quantum computing is focused on small-scale algorithm and application development and verifying that things we expect to work do work. And there have been lots of frameworks developed that are incredibly important and useful for this, and so important that our first effort was building a set of libraries to accelerate them. But there's a big gap between that work and thinking towards future hybrid performant accelerated applications that leverage the best of classical resources and quantum resources. So for that, you really want something that is able to interoperate with and leverage classical high-performance computing tools. So if you're doing machine learning, you want to make use of classical machine learning libraries. You want something that can be programmed by domain scientists. So you want something that where a quantum chemist can take their workload and start testing it on a simulated QPU or a real QPU. And you want something that is kind of optimized in its compilation to be free of bottlenecks. And so with those needs in mind, we're excited to introduce Coda. Coda is a platform for hybrid quantum classical computing built to address the challenges faced by application developers and domain scientists looking to incorporate quantum into their applications, whether through an emulated quantum processor or a physical quantum processor. Coda is open and open source. We will release an open beta in March that will be open source, and it's QPU agnostic. So it is a programming model that enables developers to write code in C++ and Python. That code is compiled by a compiler we developed called NVQ++, down to an intermediate representation where it can be executed either on a simulated backend, maybe with cuQuantum on GPUs, or on physical QPUs where we're partnering. And I'll talk about that on the next slide. Just like with cuQuantum, it's very important to us to partner with the entire ecosystem, and Coda is no different. So this list represents our initial partners. We're going to expand this dramatically, but we thought it was important to start by working with different types of quantum hardware. So you'll notice at the top there are startups representing superconducting qubits, trapped ions, photonics, neutral atoms, and NV centers. We're also working with quantum software companies developing applications on Coda and supercomputing centers who are thinking about integrating quantum computing with classical supercomputing or already doing it. So Coda is designed to be familiar to domain scientists. This very simple Hello World VQE example gives you an idea of what it looks like. The ansatz is defined as a Coda quantum kernel. The Hamiltonian is defined with this Coda spin-op function as a sum of polytensor products. You can define an optimizer with Coda and run the run VQE with a one-line call. So very simple example, but hopefully illustrates kind of what Coda looks like and how easy it is to program. And we think interoperability with classical computing software and models is going to be critical going forward. And so Coda is built to be interoperable with the best tools for high-performance classical computing, so CUDA, OpenMP, OpenACC, standard parallelism, and I'll show an example of what that looks like on the next slide. So here we're looking at an algorithm called quantum imaginary time evolution, where we gradually build up a trial quantum circuit representative of the true ground state of a specified Hamiltonian via evolution through imaginary time. So in practice, what it consists of is a step that you probably want to execute on a quantum computer computing an expectation value, which is done here with Coda spin-op. And then a step that boils down to dense linear algebra, which you'll never want to execute on a quantum computer, but is a really good fit for a GPU, and is done here with a one-line call to QSolver. So again, this is a very simple example, but already this is something that's tricky to do in other frameworks, and very, very simple in Coda. Now that we've seen a little bit about what it looks like, let's talk about performance. So we're early stages in benchmarking Coda, but already we're seeing reasons for optimism. So this is VQE again, comparing code written in Coda, compiled with NVQ++, simulated on an A100 GPU, to code written and compiled with a leading Pythonic framework, also simulated on an A100 GPU. So the hardware here is the same. This is not a GPU to CPU speedup. This is all from software. And even with 20 qubits, we're seeing almost a 300x speedup, obviously with a really nice trend as things scale. So again, early stages in our benchmarking, but a lot of reason for optimism on performance. One last example with Coda. It enables exploration of new research ideas that won't be possible for a long time. So this is VQE again, but now testing factoring the Hamiltonian and running it in parallel on many different quantum processors. And so this is something that you might want to do in the future. You can test it out in simulation today with Coda. So we ran this for a 28 qubit VQE problem representing a hydrogen chain. And we see near perfect strong scaling on 4 simulated QPUs. So again, a simple example, but hopefully is a good example of kind of novel experimentation that's possible with Coda. And we're also making progress on hardware integration. So I'm happy to say that we now have Coda running on Quantinuum's H1 processor. So this example is again, variational quantum eigensolver. On the left is a simulated result with cuQuantum. On the right is exactly the same code run on Quantinuum's H1 processor. And what's one nice thing to notice is all you do to flip the switch from simulating to running on a real processor is this compiler flag, changing it from QPU equals cuQuantum to QPU equals Quantinuum. And we expect to be able to announce many more of these in the next year. Last slide. We hope together cuQuantum and Coda are going to create a powerful platform for quantum computing research and application development. The hope is with tools like these, we can go from running proofs of concept to really making progress towards valuable quantum advantage. And this slide shows a lot of the hardware that this all runs on. One thing I often get asked is how big the team is working on quantum at NVIDIA. One answer is there are about 40 of us working full-time on quantum. But I think a better answer is what we're building depends on products that have been built over 30 years by tens of thousands of people. And we're hoping that by leveraging that and working with all of you, we can get to useful quantum computing that much faster. So that's all. Thank you for your attention. If there's time for questions.
Okay, yes, we have time for maybe 1 or 2 questions.
Hello, thank you for your presentation. My name is Dikshan, and I'm a research scientist at SoftServe. Thank you for the shout out to our work. It was a very productive collaboration using QQuantum. I'm a bit curious about what features does Coda have that QQuantum does not. I think I'm confusing these two packages separately. Could you clarify a bit on that? Thank you.
So think of Coda as another framework that sits above cuQuantum. So Coda is a programming model that allows you to program CPUs, GPUs, and QPUs all together within the same kind of framework. And so for that QPU, it can either be a simulated QPU or a real QPU. And so if it's a simulated QPU, it can have a cuQuantum backend. So they're sort of complementary. Coda leverages cuQuantum for its simulation.